Thank you so much, Michelle. I have made a note about birdcasts for our own place, so I'll be looking. Got a lot of birds at home, which is good. RMIT's Dr. Gavin Mudd is our next speaker. He's a globally recognised scholar on the environmental impacts and sustainability of mining. His research is renowned for building big data sets to assess things like declining ore grades, increasing mine waste, global mineral resources, including critical minerals, mining methods, rehabilitation and sustainability metrics, and life cycle assessment. He's worked with communities in Australia and around the world, and he joins us today to discuss encroachment on agricultural land by mining and urbanisation.
Okay, g'day everyone. It's a great pleasure to be here, and I think this talk has gone through a lot of iterations in terms of the way I guess I was thinking about it. But after hearing a lot of the talks yesterday and being reinforced this morning as well, I think I'm glad I've changed my focus a bit. But there's a few messages I want to get through. One, we're often hearing at the moment that for renewable energy, for batteries and for electric vehicles, we've got to mine more, we need more. And that's wrong. It's a myth. And it's a myth put out there to often justify the status quo. And so what I want to try and do is actually explain, well, there is, as we've heard, there's good shifts going on in agriculture. There are some good shifts happening in mining as well. And so the metals that we do need for renewable energy, for batteries and EVs, they're out there, and that's a lot of the research I do. But delete coal out of the equation and you drop, in Australia, over half of our mining industry in terms of volume and mine waste. And think about that globally as well. Roughly half of what we mine is from the coal industry. So sure, we'll mine more nickel, we'll mine more lithium and everything else. And so if I can achieve some of those things today and actually help show you the data sets that explain all of that, and then also, it's not just about mining. We also need to think about what we call the circular economy. All right, and so it's something that I've collaborated with Tom Gradle. It's been one of my great privileges in the academic work I've done to collaborate with the great-grandfather in some ways of industrial ecology and the circular economy. So normally I would spend a lot of time talking these photos and explaining them, but I'm sure some people recognize them, but just a flavor of the different ways that mining manifests, I guess, around the world. We hear this all the time. If we don't grow it, we have to mine it. Sure. We mine metals and then we can reuse them, recycle them, repurpose them, remanufacture. We can reduce the amount we use as well, right? And yes, that's true, right? But how much metals do we really have? How do we use them? And how do we intelligently make decisions about what we mine, where we mine, and how we mine? That's often the questions we don't ask. And I love using this cartoon, and I think it's probably just as relevant today as it was, 25 odd years ago. And so what we're talking about is not to stop many parts of the world from developing and saying they can't have an electric vehicle or they can't have an e-scooter. And sorry, we've run out of the metals we need for the solar panels. No, it's about actually making sure we do things efficiently within our planetary boundaries. Right. And so, and of course, the main constraint around that is climate change. But of course, it's not the only one. Right. We've probably seen these around the place and so on. And in some ways, the mining industry globally is really repositioning itself to say, well, how do we contribute to sustainable development? Globally, this is the sort of the policy language and the sort of the focus in terms of the objectives that we want to achieve globally by, say, 2030. And no poverty. Well, mining can provide some high-paying jobs, so mining can contribute to that. What about sustainable consumption? Well, sure, but which metals? Should we mine more uranium as opposed to more lithium? I'll come back to that one. But also, what about gender? Mining as an employer in some areas, of course, can play a big role in all of these sorts of things. So yes, mining has an interface with all of these things in very different ways. Some in the metals that are supplied to make the technologies to achieve these SDGs, and others it's more in some of the policies and how we go about mining. Now, I love going back through history, and it's one of the things I guess I've learned is that, that age-old cliche, if we, the one thing we learn from history is that we really don't learn from history. Now, Georgius Agricola started out life as a medical doctor. He was in what we now call the Saxon state or Saxony in eastern side of Germany. And a lot of his patients were miners. And he started realizing and thinking, well, hang on, why are so many miners getting sick? And he realized he was actually more interested in mining and metals and so on than he actually was in being a doctor. And so just the year after he died, his monograph came out. And the first chapter is, well, the philosophy of mining. Why do we bother? You can make metals or extract metals, use them to make plows and grow food, and grow it. Or you can make a sword, kill people. That duality of that use. Right? And so this is actually a really strong acknowledgement that really when mining's done badly, it not only destroys the local environment, it also destroys that local community. And I'm leaving a lot of the sort of more social side to Sally next. But now I can put a sustainability framework on this, our triple bottom line and all sorts of things, but we're still talking about these same intersection of issues right now. This is a more modern quote. D.F. Hewitt, for people who have followed the issues around peak oil and M. King Hubbert, Hewitt was his mentor. Hewitt was the one who taught him about peak metals first, and then Hubbert said, what about peak oil? All right, and I think that's a really instructive quote, because in a lot of ways, our need for food, our need for clothing and so on, that's fairly constant. But if we think about the periodic table, we're now using, if we go back, say, 200 years, we had copper, iron, gold, a bit of lead. By the turn of the 1900, of course, we've added zinc, we're just starting to add nickel. Decade later, we added aluminium. Now we add lithium, we add platinum group elements, we add the whole lanthanide series at the bottom there. So if you look at a standard smartphone, you've got 2/3 of the periodic table in that phone. 70% of the value is simply gold. Bizarre, but true. All right, and we've done some research on this over the years, and about 600 grams per tonne, 20 years ago is what a mobile phone used to have. It's down to about 250 grams per tonne now. Typical gold mine of around 2 grams per tonne. All right, so we're mining the periodic table increasingly because we want all of these funky technologies. I flew up here. The jet turbines that are in there are made with rhenium. That makes that jet super efficient, and we get our modern flying. And you could go through all sorts of other examples there, whether it's the electric vehicle, the batteries that go into the electric vehicle, or the metals that go into making those batteries and so on. So we're using more of the periodic table, more metals all the time. So where do we get them from and how do we use them? That's another sort of part of the overall question. So this is just a way of looking at what's happened with mining over the past century or so. And this is looking at it in real value. Right? This is just taking some data from the US Geological Survey and looking at the different sectors of mining. And we can see here, you've got the sort of the early parts, influence of wars, depression, etc. The post-World War II boom. Then, of course, we hit the 70s and the oil shocks and everything else. So mining went down. Then, of course, we get the big jump up on the right, the famous China boom. Went bust for a short while, but it's back, and it's back in full force. But what's interesting is that most of those metals I've mentioned, like rhenium or rare earths and many, many others, barely rate on this graph. The value of most of the metals we're dealing with are still our base metals, our copper, nickel and zinc and so on, and lead, plus things like iron ore in particular. All right, I'll come back to some of those things. So when we're thinking about mining, often there's this sort of simplistic way, they're a non-renewable resource. They're going to run out. And sure, that's true. We can find more deposits. We can learn to mine lower grades, and we've been very good at doing that. And we can keep that sort of pattern going. And historically, we've been, as a society and an industry, we've been really successful at that. So now we're able to mine vastly more, and yet we know of much, much more mineral resources in the ground than we've ever known before. Oil's probably the only exception. All right. So in some ways, we don't need to worry about resource depletion for all of these metals. What we do need to worry about is where do we mine them? How do we mine them? Right? And that's where there is good intersection with agriculture in many parts of Australia, as it is around the world. Right? But then also what we do when we're finished with those products. We'll come back to that. So I'm going to go through a lot of data, graphs and everything else, all part of the research I do. But out of all of that, hopefully the one thing that I can convince you of is that the environmental impacts per metal are going up. So for every ton of metal that we extract, it's getting harder. There's more impact, and that means more management, which, as an environmental engineer, that's in some ways good for me. It means I've got a guaranteed job for life. All right. So, but even if we mine well, we've still got to work out how we recycle and understand all of those sorts of systems. So normally I like to try and pick out a random one. Gold, we can see the yellow graph here, the gold rush of the 1800s and so on, and the gold boom of the 1980s, which was even bigger, not as heralded, but certainly bigger. Right. If we look at the red line, iron ore, it'll be 3 times higher than this chart. I deliberately haven't updated this chart because those graphs are still going up. All right. So it's pretty easy to spot the general trend. It's called exponential growth. It's what we've heard about this morning as well and yesterday. All right. So production's still going up. We're not running out, and we're not going to run out anytime soon. Now, if you look at it by value, all right, and look at year by year since about the early 1800s, we can see the initial coal that Australia started with, then a quick copper rush in South Australia. Thank you very much. The gold rush took over, Broken Hill kicked in, and so on. All right. So if we think about mining and the value and everything else, we delete coal out of the equation now, and eventually we'll get there. That's going to change the way this graph looks. And so we'll see a lot more value coming into a lot of these metals that we need for renewable energy, for batteries, EVs, and so on. All right. So when you look at it in a different way, you could look at each of the individual metals and say, the green is basically the cumulative production, like what's the total amount of production we'll eventually mined and produced so far. The red is basically what's considered economic to mine now or at that year, for example. And then the blue is basically, well, how much more is out there that we know of that is probably going to be economic in the future, but we haven't really assessed those as much yet. And so what, in some ways, the obvious pattern is they're all going up. Whoop, go back, that one, right? All going up. And some quite remarkably, others a bit flat. So we're really not running out. What we have to worry about is the mine waste we leave, the impacts on landscapes, interactions with communities, and so on. Right, but if you look at the right-hand side here, we can see a lot of these metals that we need more and more of now. So we can look at rare earths. Australia's got as much as China, pretty much. So we have opportunities here. It's not all about a negative story in some ways. All right. Now, I mentioned ore grades keep going down, and I still find it remarkable that some people in the mining industry don't think it's a problem. So I call it grade denial, right? Because it is very much like climate denial. This is a fundamental problem in the mining industry. Right. And in some ways, it's successful because we've actually been able to develop technology. Right. The geology works as you go to lower grades, the deposits often get bigger. But of course, if you're having to mine 100 tons of rock to get 1 ton of copper, that's very different to mining 10 tons of rock to get a ton of copper. And not only do we have to mine that 100 tons of rock, or ore as the industry would call it, we often have to mine another 500 tons of waste rock that has no copper in it or very little. So we've gone from an old industry that used to mine 10 or 20 tons to now mining several hundred tons for every ton of copper. All right. And so that's where that big burden comes in. And so it's pretty obvious what's happening is that grade's always going down. You can get blips here and there are all interesting stories behind those, but that general trend is fundamental. And you can see it globally from the work I've done and I'm done with colleagues. This is a global pattern. This is not something that's just unique to Australia. It's a fundamental problem in the way mining works. All right. And so when you think about it, as I mentioned, the corollary to that is in order to offset the increased cost and so on of mining lower grades, of course, we mine in open cuts. So big holes in the ground. And of course, most of that rock has nothing in it or not much in it that's worth actually extracting or processing. So you're left with this huge waste burden. And I always found it remarkable because many years ago, I got asked by a dear friend of mine who was working for the Mineral Policy Institute at the time, well, post-Johannesburg, post-2002, the industry says they're contributing to sustainable development, what we now call the SDGs. But really? Agricola noticed that there was problems, centuries ago. So, and I said, yeah, but they're not reporting waste rock much. They're not focusing on a lot of the environmental problems. They're not documenting rehabilitation properly. No one had ever put data together on it. No one. I was quite stunned. So I thought, well, good excuse for a data junkie to get to work. So I did. All right. Now, this is a slightly older version of this, but you can take all of this data and aggregate and work out how much mine waste do we really generate. Because I find it absolutely stunning that we're mining 20 billion tonnes of mine waste per year in Australia and growing exponentially, although that will drop off as coal declines. And so when we talk about waste in Australia, it's all about garbage in cities. It's about demolition waste, bio waste coming out of agriculture and things like that. They're millions of tonnes, tens of millions of tonnes. So why aren't we talking about the billions of tonnes of mine waste that sits on agricultural lands, that sits next to national parks, surrounded by Indigenous communities and things like that. So this is just the global data, and it's they're approximate. It's something like this. Imagine what happens when we delete coal. We get rid of over half of that global mine waste budget. So yeah, it's pretty simple to me. We'll increase nickel more, we'll increase lithium and things like that, but there is absolutely no way that they will be generating anywhere near as much mine waste. So we'll be better off. Right. So as I mentioned, this is a whole idea around, well, how do you actually keep the industry to account? Check the data. Spoken like a true data junkie, I guess, but it's also called good science. We need data. We need actual data. We can't just say there's no data, so therefore there's no impact. As I teach my students all the time, that's dodgy. That's not good science at all. We need good data to really understand what's happening, whether it's good or, there's impacts or not. Right. So this is just one example. It happens to be Olympic Dam. So you can look at how much ore comes through, the inputs of energy, the forms of that, and then what are the outputs, products, and also things like greenhouse gas emissions and other pollutants as well. All right. So what you can do is put all of that together, and being my engineering background, we use life cycle assessment. So we can add all of the inputs together to work out what the total outputs are. And as I mentioned, we know that if you look at ore grade, this is work for gold, we're heading downhill. So as you go lower and lower grades, you get this exponential increase, in this case, carbon dioxide emissions, but it's the same graph, obviously, for energy. So at the same time as the world wants to be more resource efficient, we want to be reducing things like our carbon, we have an inherent problem in mining where grades decline, energy and carbon goes up for the same production, and yet we're still increasing production as well. All right. That's a problem that can be solved. Electrify mining, work out more investment in renewable energy. So there's solutions out here for a lot of this sort of stuff. And I'm seeing now a lot more of that happening across mining, not only just in Australia, we're a bit behind the times compared to Chile and elsewhere, right? But we can change the shapes of these curves. We absolutely can. Now, this is something I'm going to go through pretty quickly, but it occupies a lot of my time. But when I go somewhere, I always like to go and see the local mine. And it's one of the questions people ask, where did you go on holidays? And I said, we went here. And then the next question is like, did you see a local mine? I said, yes, of course, because that's how you learn. We hear about rehabilitation all the time, and we hear about how good mining is with environmental management. So what's the actual evidence? I love getting out in the field. It's good, great fun. So this is a problem that's getting worse. More mine waste, more sulfide minerals in that mine waste means we're exposing much more rock to this process of generating acid. That acid, of course, releases salts and metals into ecosystems and communities and causes havoc. All right. And I think it's a severely underestimated problem, but that's for a paper in the very near future. And I say that because just south of here, of course, or southeast from here, you've got Captain's Flat, one on the sort of the left here. And it was rehabilitated 40 years ago, or 50 years ago, I think, actually, almost. Still got AMD going on. Certainly not as bad as it would have been without rehabilitation. And the Molonglo River, at least visually looking at it, the ecology seems okay for that. But look at other examples. Rum Jungle in the middle here, $25 million worth of federal money in the 1980s and failed within 10 years in terms of its rehabilitation. So I kind of wear it as a badge of honor that there's probably going to be another $500 million spent on working out how to clean up a mine that literally only has 10 million tons of mine waste. And this will be the second round of rehabilitation 40 years later. All right. And so there's some other examples there. And we could look at, other parts of the world. You could see, but you don't get acid mine drainage in the goldfields in Western Australia. Really? There's your classic colours of AMD. It is a huge problem. Even on green New Zealand up the top here, the old Golden Cross mine, you can still find hallmarks of it. So ultimately, almost finished. Yes, we need a lot more. Things are changing. All right. And so I mentioned this already, but some of the projections that are out there that we're seeing are huge. And again, this is just for electric vehicle batteries. So the amount of lithium and cobalt that we're going to need is going to go up by something like tenfold. Depends on your scenario, right? So we can meet that. That's not a problem. Australia's good at mining, so we can see Australia. We've already responded to that. We now know of probably something almost, would that be more than 10 times lithium than we used to know. All right. Lithium has now overtaken uranium. That is huge. That is a massive hallmark of these energy transitions that we're seeing. All right. So I mentioned this idea of a circular economy, and Barbara Reck at Yale said, well, we talk about industrial ecology, but we haven't visualized it. And so she came up with this idea of the wheel, the metal wheel. And so you can see that on the left-hand side here. All right. Now, I think other people, the Ellen MacArthur Foundation, for example, is often what's called the butterfly diagram, where we have our biomass on the left, and we've heard a lot about that over the conference, but what about all the metals on the right? And that's the sort of stuff we need to get a lot better at, including in Australia, especially in Australia, because we've got the resources, we can export stuff, but it's the manufacturing, the recycling, repurposing, all of these types of things. All right. And if you look at the global evidence, we're pretty poor at it. All right. So we don't recycle most metals yet, but we've got to get there. All right. So there are some examples. I mentioned this earlier. This is basically a mobile phone. It's rich in metals. All right. So really, really valuable. So why are we mining gold ore when we should be mining that? There we go. Done. So I'll leave it there, but thank you.
And look, thank you, Gavin, for that really robust and clear-sighted view of the reality of mining, which is something that all of us who are engaged in agriculture and environmental issues need to face up to. One question, go ahead.
Can you talk about a more refined mining approach? Like what is the opportunities for refining in situ to get through the low ore grade issues?
The potential ways we can change mining vary depending on which element you're looking at, but there are certainly better ways to process. Sometimes there's not as many options when it comes to the actual mining of the rock itself. So it's either open cut or underground, but certainly there are ways to come up with better processing. But also it links back into some of the downstream end as well, like the smelting and refining, which is not something we have a lot of here in Australia. So, and I think when you're looking at the value chain, Australia is something like 70% of global lithium production now, and yet we're 1% of the value chain. All right. And that's crazy. Like, why are we, exporting dirt and then buying back expensive diamonds? It's really stupid. But we've been doing that for 2 centuries worth. So it's and we need to change that paradigm. As much as we talk about changing the paradigm in agriculture, we really have to change that. And so by changing some of the processes in mining, we can maybe incorporate better refining capacity here in Australia and link that into our manufacturing as well. So and that's some of the work, I guess, that's very much ongoing.
Great. Thank you so much.